Every atom in your body has a birthday. The carbon in your bones, the oxygen in your lungs, the iron in your blood, every single one of those atoms traces its origin back to a single moment 13.8 billion years ago. Not to a star, not to a planet, not to a galaxy, but to one event, one beginning, from which everything that has ever existed emerged. This video is the story of that beginning. Not just the first billion years, not just the first million years, but the first second, the first 20 minutes, the first few hundred million years, and what all of it means for why anything exists at all. It is the most ambitious story science has ever tried to tell, and the remarkable thing is that we can actually tell most of it with real evidence, real measurements, and real physics. We just have to be honest about the few places where the story hits a wall, and we genuinely do not yet know what lies on the other side. Let us start at the very beginning, and let us start with that wall. The first moment of cosmic history has a name. It is called the Planck epoch, and it lasted from the instant of the Big Bang at time 0 until roughly 0.054 seconds later. Written more cleanly, that is 5.4 times 10 to the power of negative 44 seconds. It is an interval of time so short that if you tried to count it by splitting every second into a billion pieces and then splitting each of those pieces into a billion more pieces, and kept splitting like that again and again many times over, you would still not have divided time finely enough to measure it. And kept splitting like that again and again, many times over, you would still not have divided time finely enough to measure it. During that unimaginably brief instant, the entire observable universe, everything that now stretches more than 93 billion light-years across space, was compressed into a region smaller than the Planck length of about 1.6 times 10 to the power of negative 35 meters. To put that in perspective, a proton is already almost incomprehensibly small. The Planck length is to a proton what a proton is to the entire visible cosmos. Temperatures soared above 10 to the power of 32 Kelvin, and densities exceeded values so extreme that every number we might write down for them loses physical meaning. At those conditions, something profound was true about the universe. The four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, are believed to have existed as a single unified interaction. The very distinction between space-time and quantum fields dissolved. Quantum fluctuations of gravity itself would have dominated the behavior of the universe, making the smooth, classical picture of space-time that Einstein's general relativity describes completely meaningless. And here is where the honest wall appears. General relativity cannot describe this regime because it assumes space-time is a smooth, continuous surface. Quantum field theory cannot describe it because it assumes a fixed background space-time to work on. Neither theory works. String theory and loop quantum gravity are the leading candidates for a theory of quantum gravity that could describe this era, but both remain incomplete, and neither has been tested at these energies. The Planck epoch is therefore exactly like a locked room at the very beginning of time. We can press our ear against the door and hear muffled clues in the form of theoretical consistency requirements and indirect predictions, but we possess no tool in current physics capable of turning the handle and actually entering. Max Planck himself, when he derived the natural units of length, time, mass, and temperature that now bear his name in his 1899 work, was simply building a system of measurement based on fundamental constants rather than human artifacts. He could not have imagined that those units would one day define the outer boundary of human knowledge about the beginning of the universe. After the Planck epoch, from about 10 to the negative 43 seconds to about 10 to the negative 36 seconds, the universe entered what physicists call the grand unification epoch. Gravity had separated from the other three forces at the close of the Planck era. What remained was a single grand unified force combining electromagnetism with the strong and weak nuclear forces into one interaction. Temperatures were still above 10 to the power of 29 Kelvin, and particle energies reached values more than 1 trillion times higher than anything the Large Hadron Collider can achieve today. The theoretical framework suggesting these three forces could be unified came from Howard Georgi and Sheldon Glashow at Harvard University, whose 1974 paper in Physical Review Letters introduced an SU-5 model demonstrating how the strong, weak, and electromagnetic forces could arise from a single gauge symmetry. As the universe expanded and cooled, at around 10 to the negative 36 seconds, the strong nuclear force separated from the electroweak force in a spontaneous symmetry-breaking phase transition. Think of it this way: liquid water looks completely identical in every direction and possesses a high degree of symmetry. When that water freezes into ice, the crystals form along specific directions, and the original symmetry is broken. The forces of nature crystallized out of their unified state in precisely the same way as the cosmos cooled, each acquiring its own distinct properties. That symmetry breaking is also thought to have released enormous energy that may have triggered what came next, which is one of the most extraordinary events in the entire history of the universe, beginning around 10 to the negative 36 seconds and lasting until roughly 10 to the negative 32 seconds. The universe underwent a period of exponential expansion called cosmic inflation. During this window of time, shorter than any number we can meaningfully speak aloud, the scale of the universe grew by a factor of at least 10 to the power of 26. In many models, it grew by 10 to the power of 60 or far more. The idea was first proposed by Alan Guth at the Massachusetts Institute of Technology in his landmark 1981 paper in Physical Review D, later refined by Andre Linde at Stanford University, and independently by Andreas Albrecht and Paul Steinhardt at the University of Pennsylvania in 1982. Together, their work solved three deep puzzles that the standard Big Bang model had left completely unexplained. The first puzzle is called the horizon problem. Look at the cosmic microwave background, the oldest light in the universe, and measure its temperature in two opposite directions of the sky. The temperatures match to within 1 part in 100,000. But without inflation, those two regions of the sky were so far apart that light could never have traveled between them. Inflation solves this by pointing out that before the expansion, those regions were once right next to each other and had time to reach the same temperature. The second puzzle is called the flatness problem. The universe's spatial geometry today is extraordinarily close to perfectly flat. For the universe to be as flat as we measure it today, it would have had to be tuned to flatness in its earliest moments to within 1 part in 10 to the power of 60 or more. That level of precise fine-tuning seems absurd without a physical mechanism to explain it. Inflation provides that mechanism by stretching any initial curvature to such enormous scales that it becomes undetectable, like stretching a crumpled piece of paper until it looks perfectly smooth. The third puzzle is the monopole problem. Grand unified theories generically predict the production of exotic particles called magnetic monopoles in enormous quantities during the GUT scale phase transition, yet none have ever been observed. Inflation dilutes any monopoles produced before its end to such a tiny density that the probability of finding one in the entire observable universe becomes essentially zero. The engine of inflation was a hypothetical scalar field called the inflaton, whose potential energy dominated the cosmic energy budget and drove the exponential expansion. When the inflaton field eventually rolled down to the minimum of its potential, inflation ended and its energy was converted into a hot plasma of particles and radiation through a process called reheating, igniting the hot Big Bang phase we normally think of as the beginning of the universe. But here is the part of inflation that connects directly to everything you see in the night sky. During inflation, quantum fluctuations in the inflaton field were stretched from subatomic scales to macroscopic wavelengths and became the primordial seeds of all cosmic structure. Those tiny quantum ripples, frozen into the fabric of spacetime by inflation, later grew under gravity into galaxies, clusters, filaments, and voids. The cosmic microwave background measurements from Planck confirm this picture beautifully, yielding a scalar spectral index of approximately 0.965, consistent with the simplest inflationary models. Think of inflation as someone rapidly inflating a tiny, heavily wrinkled balloon to the size of the observable universe. The exponential stretch smooths every wrinkle until the surface appears perfectly uniform to the eye. But under a sufficiently powerful microscope, the faintest residual traces remain visible as temperature ripples across the sky. The cosmic microwave background is that microscope, and the ripples it shows us are the stretched ghosts of quantum fluctuations from the birth of the universe. At about 10 to the negative 12 seconds after the Big Bang, when the temperature had fallen to around 10 to the power of 15 Kelvin, the electroweak force underwent its own phase transition, splitting into the distinct electromagnetic and weak nuclear forces. At this moment, the Higgs field, which permeates all of space, acquired a non-zero value of about 246 giga-electronvolts, and elementary particles acquired their masses through the Higgs mechanism. The theoretical foundation was laid in 1964 by Peter Higgs at the University of Edinburgh and independently by François Englert and Robert Brute at the Université Libre de Bruxelles. Experimental confirmation came in 2012 when the ATLAS and CMS collaborations at CERN's Large Hadron Collider announced the discovery of the Higgs boson at a mass of approximately 125 giga-electronvolts, earning Higgs and Englert the 2013 Nobel Prize in Physics. Before this moment, particles were massless. After it, the universe had structure, weight, and the foundations of chemistry. From about 10 to the negative 12 seconds until about 1 microsecond after the Big Bang, the universe existed as a hot, dense soup of free quarks, gluons, photons, leptons, and their antiparticles, a state called the quark-gluon plasma. Temperatures exceeded roughly 2 times 10 to the power of 12 Kelvin. This state has actually been recreated in Earth laboratories. At CERN's ALICE detector, at the Large Hadron Collider, and at Brookhaven National Laboratory's Relativistic Heavy Ion Collider, by smashing heavy atomic nuclei together at nearly the speed of light. The results from ALICE showed that the quark-gluon plasma behaves as a nearly perfect liquid with the lowest viscosity to entropy ratio ever measured in any fluid. At about 1 microsecond after the Big Bang, the temperature dropped below the threshold where the strong force could no longer keep quarks free. Quarks bound together into color-neutral hadrons, primarily protons and neutrons, in the QCD phase transition. And at that moment, the most consequential question in the history of the universe was being settled. Equal numbers of particles and antiparticles had been created in the hot primordial plasma. As the temperature fell, they met each other and annihilated in pairs, converting their mass entirely into photons. A universe of pure radiation was threatening to emerge with no matter left at all. But there was a tiny imbalance. Roughly 1 extra matter particle existed for every billion matter-antimatter pairs. That 1 in a billion surplus survived the annihilation and constitutes every proton and neutron in the universe today. Every star, every planet, every atom in every living thing on Earth descends from those survivors. The conditions required for such a baryon asymmetry were first identified by Andrei Sakharov in a 1967 paper in JETP Letters, who showed that any explanation must involve violation of baryon number, violation of charge parity symmetry, and a departure from thermal equilibrium. The standard model of particle physics does contain CP violation, but its magnitude falls short of what is needed by roughly 10 orders of magnitude. 1 microsecond after the Big Bang, the universe had protons and neutrons. That is a genuine milestone, but it is not yet a universe of atoms or chemistry or anything that could one day build stars. The protons and neutrons were still too hot, still moving too fast, still embedded in a plasma, too energetic for any two of them to stick together and form a nucleus. The universe needed to cool down further, and the next 20 minutes of cosmic history would accomplish something that no process has ever repeated since. In those 20 minutes, the universe cooked the hydrogen and helium that still make up 99% of all ordinary matter today. The ratios it produced are baked permanently into every star, every galaxy, and every nebula in the observable universe. Getting those ratios right is one of the most powerful confirmations that the hot Big Bang model is correct. At approximately 1 second after the Big Bang, the temperature had dropped to around 10 billion Kelvin, corresponding to particle energies of about 1 mega-electronvolt. At this temperature, the weak nuclear force, the force responsible for radioactive beta decay and for the interactions of neutrinos, had become too slow to keep pace with the rapid expansion of the universe. Neutrinos decoupled, meaning they stopped interacting with the rest of the plasma almost entirely and began streaming freely through space. They have been doing so ever since. Right now, as you watch this video, roughly 330 neutrinos from the Big Bang itself are passing through every cubic centimeter of space around you, an invisible cosmic neutrino background predicted in detail by Steven Weinberg in a 1962 paper in Physical Review. An experiment called Ptolemy at Princeton University is attempting for the first time to capture relic neutrinos through their interaction with tritium atoms. Detecting the cosmic neutrino background would be one of the greatest experimental achievements in the history of physics. About 10 seconds after the Big Bang, the temperature dropped below roughly 5 billion Kelvin, equivalent to about 0.5 mega-electron volts per particle. This threshold is important because it corresponds to the rest mass energy of an electron. Below this temperature, electron-positron pairs could no longer be produced from the photon bath. The existing electron and positron populations annihilated each other, converting their combined mass into additional photons. Because neutrinos had already decoupled and were no longer in contact with the photon bath, they did not share in this infusion of energy. As a result, the photon temperature was boosted relative to the neutrino temperature by the precise factor of the cube root of 11 divided by 4. This is not a detail, but a direct thermodynamic prediction of the expanding universe, and the fact that the cosmic microwave background temperature today is about 2.725 Kelvin, while the neutrino background is about 1.95 Kelvin reflects this exact relationship, preserved across 13.8 billion years of cosmic expansion. Now, the nuclear kitchen opened. From roughly 10 seconds to about 20 minutes after the Big Bang, the universe was hot and dense enough for nuclear fusion reactions to proceed, but cool enough for the products to survive without being immediately blasted apart again. This period is called Big Bang nucleosynthesis, and it represents one of the most precisely understood events in all of cosmology. The story begins with the neutron-to-proton ratio. At about 1 second, when the weak interactions froze out, there was roughly 1 neutron for every 7 protons. This ratio was set by 2 things: the temperature at which the weak interactions froze, and the small but critical mass difference between the neutron and proton of 1.293 mega-electron volts. Free neutrons are unstable and decay into protons with a mean lifetime of about 610 seconds, roughly 10 minutes. So any neutron that did not get incorporated into a nucleus within about that time would simply disappear. This created a ticking clock. The first step in building nuclei was forming deuterium, a nucleus containing 1 proton and 1 neutron bound together. Deuterium is fragile. The photon bath in the early universe was so intensely energetic that any deuterium nucleus that formed was immediately blasted apart by a high-energy photon. This is called the deuterium bottleneck, and it prevented nucleosynthesis from proceeding until the temperature dropped below about 1 billion Kelvin, roughly 3 minutes after the Big Bang. Once deuterium could survive, a rapid sequence of fusion reactions built up helium-4, the most stable of the light nuclei, consuming almost all the available neutrons. The remaining protons were left as hydrogen. Trace amounts of deuterium, helium-3, and lithium-7 were also produced as byproducts. The foundational calculation of this process was presented by Ralph Alpher, Hans Bethe, and George Gamow in a 1948 paper in Physical Review. Gamow, who possessed an irrepressible sense of humor, insisted on including the name of his colleague, Hans Bethe, in the author list, even though Bethe contributed no direct calculations, simply because the resulting author sequence of Alpher, Bethe, and Gamow matched the first 3 letters of the Greek alphabet: alpha, beta, gamma. The physics behind the joke was completely serious. Standard Big Bang. Nucleosynthesis predicts that approximately 75% of ordinary matter by mass should be hydrogen, and approximately 25% should be helium-4. Observations of very old, metal-poor stars and primordial gas clouds confirm these proportions to high precision. This agreement between a calculation done in 1948 and measurements made billions of years later across the entire observable universe is one of the most compelling confirmations that our model of the early universe is fundamentally correct. There is one exception. The predicted abundance of lithium-7 is roughly 3 to 4 times higher than what is actually measured in the oldest, most metal-poor stars in our galaxy's halo. This is the lithium problem, and as of mid-2026, it remains genuinely unresolved. It might reflect systematic errors in how we model the surfaces of very old stars where lithium measurements are taken. It might reflect some physical process that depleted lithium from the surfaces of those stars over billions of years, or it might point to new physics during nucleosynthesis that the standard model does not yet capture. Nobody knows. The universe's first nuclear kitchen was open for only about 17 minutes. In that window, it cooked hydrogen and helium in precisely the proportions we observe today, then closed forever, leaving all heavier elements to be forged much later inside stars. The lithium problem is a small but persistent smudge on an otherwise beautifully clean experimental conformation. After nucleosynthesis ended at about 20 minutes, the universe entered a long, uneventful era dominated by radiation. For the next 380,000 years, the cosmos was an opaque plasma. Protons and helium nuclei moved through a sea of free electrons, and photons scattered off those electrons so rapidly and so continuously that light could not travel in a straight line. The universe was completely opaque, filled from edge to edge with a glowing fog of plasma through which no light could escape. Then, at approximately 380,000 years after the Big Bang, the temperature dropped to about 3,000 Kelvin. At this temperature, electrons were moving slowly enough to be captured by protons and helium nuclei and form neutral atoms. This process is called recombination, though the name is slightly misleading because these particles had never previously been bound together. There was nothing to recombine from. The accurate name should really be combination for the first time, but recombination is what stuck in the textbooks. When neutral atoms formed, the free electrons that had been scattering photons in every direction were suddenly absorbed into atoms. The plasma became a neutral gas, and the universe went from opaque to transparent almost instantly on cosmic timescales. The photons that had been trapped in the plasma were released and began streaming freely through space. Those photons are still traveling today and make up the cosmic microwave background radiation, the oldest light in the observable universe. The photons that had been trapped in the plasma were released and began streaming freely through space. Those photons are still traveling today and make up the cosmic microwave background radiation, the oldest light in the observable universe. The theoretical description of recombination was developed independently in 1968 by P.J.E. Peebles at Princeton University and by Yakov Zeldovich and colleagues in Moscow. But the cosmic microwave background itself was not detected until 1964, when it was discovered by accident. Arno Penzias and Robert Wilson at Bell Telephone Laboratories in New Jersey were commissioning a highly sensitive horn antenna originally built for satellite communications work. They detected a faint, persistent, isotropic hiss of microwave noise at a temperature of about 3.5 Kelvin that refused to go away no matter which direction they pointed the antenna. They checked every possible terrestrial and instrumental source. They inspected the antenna repeatedly. They even cleaned out a pair of pigeons that had nested inside it and coated the interior with what they diplomatically described as a white dielectric material. The noise remained. They could not explain it. The COBE satellite, launched in 1989, measured the spectrum of the cosmic microwave background and found it to be an almost perfect blackbody at 2.725 Kelvin, matching the theoretical prediction with extraordinary precision. COBE also detected for the first time the tiny temperature fluctuations across the sky at the level of 1 part in 100,000, the imprints of those original quantum fluctuations stretched by inflation and later amplified by gravity. When George Smoot announced this detection in 1992, he said that if you are religious, it is like looking at God. He and John Mather shared the 2006 Nobel Prize. The Planck satellite, launched in 2009 by the European Space Agency, mapped these temperature fluctuations with extraordinary precision across the entire sky, delivering the most precise measurements of cosmological parameters ever achieved. The universe is 13.797 billion years old. The Hubble constant is 67.4 kilometers per second per megaparsec. Ordinary matter makes up 4.9% of the total energy budget, dark matter 26.8%, and dark energy 68.3%, with spatial geometry consistent with perfect flatness to within 0.2%. All of this from the temperature pattern of light emitted 380,000 years after the Big Bang. The cosmic microwave background is the baby picture of the universe, a snapshot taken when the cosmos was only 380,000 years old, showing the faint spots that would grow over billions of years into every galaxy, every star, and every planet that has ever existed. After the cosmic microwave background photons flew free at 380,000 years, the universe entered a period that astronomers call the cosmic dark ages, and the name is completely literal. There were no stars, there were no galaxies, there were no sources of light of any kind anywhere in the cosmos. The photons of the CMB, having just been released, were rapidly redshifting from visible orange-red wavelengths into the infrared and then into the microwave regime as the universe expanded. The gas was cooling from 3,000 Kelvin toward hundreds and then toward tens of Kelvin. The universe was dark, cold, and silent in every direction, filled only with vast clouds of neutral hydrogen and helium gas slowly responding to the pull of gravity. It was like the universe holding its breath. Every ingredient for what was coming was already in place. The dark matter halos were beginning their slow gravitational growth. The seeds of structure planted by inflation were present in the tiny density variations of the gas, but the first spark of light had not yet been struck. This long darkness lasted from about 380,000 years after the Big Bang until somewhere between 100 million and 200 million years, when conditions finally became right for the first stars to form. During those hundreds of millions of years, dark matter played a crucial and invisible role. Because dark matter does not interact with light or electromagnetic radiation, it had been free to begin clumping gravitationally even before recombination, building up dense halos, while ordinary matter was still locked in the plasma. After recombination, ordinary gas began falling into those dark matter halos, compressed and heated as it fell. The first halos, massive enough to retain gas against the heating and begin forming stars, had masses of roughly 100,000 to 1,000,000 times the mass of our Sun, and they assembled at cosmological redshifts between about 20 and 30. Whereas Bratzerels, Bratzerber, and der Rau. Ifri, Amberder, the Courier, the Ster Ain and Terrainwar, non Dairy. Corresponding to times between roughly 100 and 200 million years after the Big Bang. The first generation of stars that formed from this primordial gas were utterly unlike any stars that form in the universe today. And the reason comes down to chemistry. The gas available to those first stars contained only hydrogen, helium, and trace amounts of lithium. No carbon, no oxygen, no silicon, no iron, nothing that astronomers call metals, meaning every element heavier than helium. This matters enormously for star formation because heavy elements are the primary cooling agents in modern molecular clouds. When interstellar gas, rich in carbon and oxygen, falls together under gravity, those molecules radiate energy away as infrared light, allowing the gas to cool and fragment into relatively small, dense clumps. Those small clumps become stars of modest mass, similar to, or smaller than, our own Sun. But primordial gas with no heavy elements at all could not cool efficiently through molecular radiation. It had to cool primarily through the much less efficient process of hydrogen and helium gas radiating, which required much higher temperatures and densities before fragmentation could occur. The result was that the first gas clouds did not fragment into small clumps. They collapsed into enormous, massive fragments far larger than anything forming today. Pioneering numerical simulations of this process were performed by Volker Braun, Paolo Coppi, and Richard Larson, and independently by Tom Abel, Greg Bryan, and Michael Norman, published in 2002. Both groups followed the collapse of primordial gas clouds inside dark matter halos in extraordinary computational detail, tracking the chemistry, the cooling, the fragmentation, and the eventual condensation of gas into protostellar objects. Their results converged on a consistent picture. Population 3 stars typically ranged from 30 to 300 solar masses, with some models extending the upper limit toward 1,000 solar masses or more. These were not slightly larger than modern stars. They were monsters. A star of 300 solar masses generates a luminosity reaching millions of times that of our Sun. its surface temperature would be 50,000 to 100,000 Kelvin, hot enough to radiate intensely in the ultraviolet, and these stars burned through their fuel at a catastrophic rate. Volker Braun has reflected that the first stars marked the end of the cosmic dark ages and transformed the universe from a simple, homogeneous state into one filled with complex structure and heavy elements. They were cosmic bonfires, that der or Aufrauers, so blindingly brilliant that they burned through the fog of the dark ages and illuminated the cosmos for the first time. No population 3 star has ever been directly observed. All of them lived and died billions of years ago. Direct detection of an individual population 3 star remains one of the primary objectives of the James Webb Space Telescope, though even JWST cannot resolve individual stars at the redshifts where the first generation lived. What JWST can do is observe extremely distant, metal-poor galaxies in the process of assembling and look for the spectral signatures of stellar populations dominated by very massive hot stars. Meanwhile, the chemical evidence for the first stars is preserved in the oldest surviving stars in our own galaxy's halo. In 2002, Norbert Christlieb and colleagues discovered a star called HE01 07-5240, whose iron abundance is less than 1/200,000th of the solar value. Its chemical composition bears the fingerprint of a particular kind of supernova explosion, providing indirect but compelling evidence that the very first stellar generation really did exist and really did explode in the ways our models predict. The deaths of the first stars were as extreme as their lives, and they varied dramatically depending on mass. Stars between approximately 140 and 260 solar masses are predicted to die in a type of explosion called a pair instability supernova. At the extreme temperatures in the cores of such massive stars, photons begin spontaneously converting into electron-positron pairs. The core begins to collapse, triggering a thermonuclear runaway that obliterates the entire star with no compact remnant left behind. These explosions disperse the first heavy elements, carbon, oxygen, silicon, iron, and others, into the surrounding intergalactic medium for the very first time. Stars above 260 solar masses are predicted to collapse directly into black holes, potentially providing the seeds for the supermassive black holes that today sit at the centers of most large galaxies. Stars below about 140 solar masses ended as conventional core collapse supernovae. All of these processes together enriched the intergalactic gas with the first metals, making the formation of subsequent smaller, cooler, longer-lived population 2 stars possible and initiating the sequence of stellar generations that eventually produced the Sun. With the ignition of the first stars came the beginning of a transformative period in cosmic history called the Epoch of Reionization. The intense ultraviolet radiation from those first massive stars was energetic enough to strip electrons from the surrounding gas. As more and more stars and the first galaxies formed, these ionized bubbles grew larger, eventually overlapping and merging until the entire intergalactic medium had been stripped of its electrons and rendered ionized once more, bringing the universe back to a state of transparency after the long, dark silence. This process was not instantaneous or uniform. It was patchy and gradual, driven by the uneven distribution of the first luminous sources. The evidence for reionization is written in the spectra of distant quasars. James Gunn and Bruce Peterson predicted in 1965 that if the intergalactic medium were neutral, it would absorb light, producing a complete dark trough in quasar spectra. Observations show exactly this signature appearing fully at redshifts above about 6. The Planck satellite's measurement implies that the midpoint of the reionization process occurred near redshift 7.7, roughly 700 million years after the Big Bang. The 21-centimeter hyperfine transition of neutral hydrogen offers a direct probe of the neutral gas during the Dark Ages. An experiment called EDGES reported a tentative detection in 2018, but the result has not been confirmed. The James Webb Space Telescope has transformed our understanding of the earliest galaxies. As of 2024, the most distant spectroscopically confirmed galaxy is JADES-GS-Z14-0, existing at a redshift of approximately 14.2. Before JWST, detecting a galaxy at this epoch would have been considered essentially impossible, but JWST has found objects that are brighter and more massive than virtually all pre-launch theoretical models predicted for this epoch. The universe appears to have built large, luminous structures far earlier than our models expected. It is rather like opening a baby photo album and unexpectedly finding pictures of teenagers. Whether this reflects a need to revise how we model the physics of star formation, or whether it points to something deeper about the underlying cosmological model, is currently an open and actively debated question. We have now followed the universe into the first blazing light of the first stars. The theoretical framework we use to describe almost all of it, a model called lambda-CDM, has been tested and has passed essentially all of them. Lambda-CDM is the standard model of cosmology. It describes a universe dominated by dark energy and dark matter. The entire observable universe in this model can be characterized by just 6 numbers. The 2018 Planck measurements yield the age of the universe as 13.797 billion years, the Hubble constant as 67.4, and spatial flatness to within 0.2%. It stands as one of the greatest achievements in the history of human knowledge. And yet, there are cracks, and they are real, and they are important. The most persistent and most discussed discrepancy is called the Hubble tension. The Hubble constant measures the current rate at which the universe is expanding. From Planck satellites' CMB data, you get approximately 67.4. When measured directly using Cepheid variable stars, you get approximately 73. That difference corresponds to a statistical disagreement of between 4 and 6 sigma. 2 independent measurement methods are pointing the same tape measure at the same hallway and getting answers that differ by 8%. Adam Rees has described the situation as potentially the first real clue we have gotten about the nature of dark energy in 25 years. Recent JWST observations have helped rule out common systematic errors. In the context of dark energy, the most exciting recent development comes from an instrument called the Dark Energy Spectroscopic Instrument, or DESI, building the largest three-dimensional map of the universe ever constructed. In April 2024, DESI released results showing hints that dark energy may be evolving. In March 2025, with more data, the preference for evolving dark energy strengthened to as high as 4.2 sigma. If the signal holds up, it would represent the first major empirically driven departure from the simplest lambda-CDM framework in decades, with profound implications for how the universe will ultimately end. Beyond the Hubble tension, a longer list of deep problems remains open. The nature of the inflated field, the search for primordial gravitational waves, and the origin of the matter-antimatter asymmetry remain among the deepest mysteries. That next generation of instruments is being built right now. CMB-S4, Lightbird, the Square Kilometer Array, the Vera Rubin Observatory, Euclid, and LISA promise a transformative decade. LISA will detect gravitational waves from massive black hole mergers, opening a gravitational window onto epochs that no electromagnetic telescope can reach. These instruments will keep the next generation of scientists busy for decades. You are made of the universe looking at itself. The carbon in your body was forged inside stars that lived and died billions of years before the sun was born. The hydrogen in your water was produced in the first 20 minutes of cosmic time. The protons in your body are survivors of the great matter-antimatter war of the first microsecond. Carl Sagan put it simply, the cosmos is within us. We are made of star stuff, and we are a way for the universe to know itself. The story started in the first second, and we are still in the middle of it.